Okay, that's good. Let me share my screen. Yes. Can you see my presentation? Can you see my presentation?
Yes, I can see the PowerPoint.
Okay. So I'm going to talk about a little bit about QWord and this QCousins program that QBrazil is going to join. It's about building a global network of quantum computing groups. My name is Ioannis Theodonis. I told you I'm from Greece, Q Greece, actually the cousin from Greece. And I also work as a physics instructor in the National Technical University of Athens. QWord is a great community with a goal to build an open and inclusive ecosystem of quantum technologies. And we welcome everybody who is a quantum enthusiast, eager to learn and participate in different projects that we are doing. And we are eager to, spread the word around the world. So with the Q Cousins program, we try to motivate people to spread the word around the world. This is what we're doing here also. And we have actually some coordinators for this QCasm network. Pavel now is the coordinator, I think, or Lorraine is a sub-coordinator. We are a group of people. So what we do is we organize workshops. Every QCasm organize workshops like this. The first one is a co-organization with us, with the QCasm's department, but the next ones will be organized by your group. QBronze is the introductory one. We have the silver one with solar algorithm. We have also nickel and cobalt. You have also classes that you can have courses and you can do also nice cool stuff like game jams and quantum games and participate in hackathons and really good stuff. When you start, you don't want to get out of this game. Why should we build a quantum ecosystem? Because we need more talented people at the end. I'm not going to read all this. But
Sorry, Ioannis. If you're going through the presentation, we cannot see. We only see your first slide.
really? Oh,
Yes.
sorry.
Sorry, I
So,
thought I didn't notice also that you're going through your presentation.
oh,
It's not
okay.
on presentation
But I
mode.
was going very fast, so maybe I
Okay.
did here.
You're 30.
Uh,
Okay. Now we can see the.
okay, okay. Maybe, but maybe it's not showing on the full screen. Sorry about that.
Yeah. And we're stuck in the first one.
Yeah. So I was talking about the Q cousins. Okay, so this is the Q Greece example. And we are doing the workshops, as I told you. Sorry about that. And the silver one is going to be organized next. This is a more serious one. The first one is the introductory. We will show QFT here and source algorithm. And the nickel is also interesting. With Deutsch algorithm and Bernstein-Vazirani algorithm and Simons algorithm, Grover's max cut problem. And I was telling you about these courses that we have every year now, and you can join. Also, we have the Q intern program where we have students at the end of the year participating in research activities. And we also go to hackathons, I told you, in groups and quantum games and stuff like that. And we need talented people to join in the quantum ecosystem. So join us and follow the social media everywhere and spread the word. And I hope you enjoy this workshop. And that's all from me. So I give I stop sharing. And now you can start presenting the going to be QBrazil team if you want, Bruna.
For sure. Thanks for your presentation, Yanis. Let me try to share my screen. Okay, I guess I am in presenter mode. Okay, so thanks everyone for joining us. Just want to talk a bit more of QBrazil, how it started, how we're thinking of going about QBrazil. So how it started? Well, it started because of all this influence from keyword that Ioannis was just talking about. Me and the other people involved in the participation, we knew from keyword. I think pretty much everyone here participated of some instance or another, either QBronze. I myself participated of Q intern, and it was very fun, very nice hands-on experience with computing that I think really changed the trajectory of my career. It got me really involved with the topic. And Keyword has this very nice idea of bringing the content for free and very accessible to everyone. And this really resonated to us. And earlier this year, I managed to meet some of the Keyword people, and Ioannis, for instance, some of the other people involved with keyword creation or any other aspect of it. And we clearly have common interests, common missions. And in particular, QBrazil, the idea to be one of the different cousins, one of the different countries involved in keyword. And we have some particular missions here. Let me see. Oh, it's weird. I cannot slide very well here. Sorry, I don't know what's going on. Okay, yeah, let me go like this. Our idea as a QBrazil in particular is to empower the Brazilian population scientifically. So one of the concerns that we have is the lack of content in Portuguese for about quantum, right? This event in particular, we also trying to do a mix of Portuguese and English. So sorry if you don't speak Portuguese, but this is part of our ambition to bring more content because we really have a lack of content in Portuguese, high quality content. So we want to combine both of the missions, Keywords mission and our vision for Brazil in particular. So increase Brazil's presence in global conversations on quantum, policy conversations, to be there participating more actively, right? And we also believe that the promoting of technologies in general, but quantum technologies can be a tool for social good, social prosperity. And we also are really aligned with Keyword with the idea of promoting open and free code to improve education. So that's what we're going for. How's it going so far? This first event that we have, the Entangling Workshop, is our first event to actually join Keyword, and we're very happy with the results. We have more than 300 applicants, around 17% women, which we could improve. But that's kind of also the statistics that we have for women in physics, for instance. But this is something that we're thinking later on how to really improve to access minorities, for instance. And really align with the idea of getting of democratizing quantum knowledge. And we had applications from many different countries like Brazil, Portugal, Argentina, Canada, many countries, and we're very happy to see the very positive response to this event. And I'll talk a bit also who we are, the six of us for now. Raíssa Brutaca, she has a PhD in physics from University of São Paulo. She studied, she had her postdoc at Technical University of Denmark studying quantum sensing, one of the quantum technologies that we have. And she's doing R&D, research and development, as an optical engineer at NQT Photonics in Denmark right now. Arthur, he's from Rio de Janeiro. He's finishing his PhD in out of equilibrium quantum systems, jointly with Unicamp from Brazil and University of Stuttgart in Germany. and he's working at Pascal, Netherlands, as a quantum and AI expert. Rodolfo holds a PhD in thermodynamics of quantum control, and is currently a postdoc research at IQC, the Institute of Quantum Computing and Perimeter Institute, both in Canada, Waterloo, Canada. Crisia, she's a professor at the São Carlos Institute of Physics in Brazil. Her research is in condensed matter and quantum information, and she is also a big firm believer of outreach as an important component of science. Bruna, that's me. I'm staff scientist in quantum technologies in Canada. I have a PhD in physics from University of São Paulo with a Sunday period in Denmark, and I'm also a science communicator, try to popularize quantum both in Portuguese and English. And Letícia, she's from Pernambuco, Brazil as well. She's graduated in University of São Paulo, molecular sciences. She has participated in many different research programs related to quantum during her undergrad. And she's now working at Brazil Quantum Institute, one of our later talks in this event, in researching quantum-based commitment. So many different backgrounds, but also kind of similar backgrounds. Very glad to be working with all of you. But of course, if you want to help engage in this mission of popularizing quantum technologies, in particular to Portuguese-speaking countries and Brazilian, in the Brazilian context, I think we really would love to have your help. We need help translating. We need help just spreading the word. It will be very nice. So you can also send us an email or reach out to us through Discord, for instance. And that's it. Thank you, or how would you say in Portuguese? Obrigada for participating
Obrigada.
and engaging. Yes, yes. Okay, so I
Thank
think
you, Bruna. And
thank you.
great work. The team looks very good, and you guys
Yes.
will take it far. I'm very sure. I'm very proud of you already. And
Oh, thank you.
we thank all our participants for joining so many great numbers. Good job for the team already. And Kenneth, would you like to present yourself also? Our instructor, Kenneth, is Amade. Can you hear us? Or will you start directly with the hard math?
Yeah, like I'll definitely jump into the content like right
Okay.
now. But okay, so hello everyone. I am Kenneth Samadi. I am a software developer from Nigeria, and I'll be your instructor for the workshop.
Thank you, Kenneth, for being such a good instructor for us. Will you also please explain the canvas and so on, the typicalities and or should I do that? I think you can handle it better than me.
Yeah, sure. I can show them everything concerning Canvas.
Because
Okay,
I
so
believe
like
you guys have received an email already, invitation to the canvas. Okay, and Kenneth will take you.
yes, so I've sent out the emails. So check to see if you've gotten the Canvas invitation. And if you haven't, reach out to us on Discord. So when you receive the email, so this is QWorld's hosted version of Canvas. So don't attempt to use login details you've used for a different course here. If you haven't participated in a QWorld workshop previously, you need to create a new account. So once you've been granted access, you will be directed to the homepage. And these are the main things you should know about the assignments for the workshop. So there are 5 days and an assignment for each day. So you need to score at least 10 in each day's assignment. So, okay, let me move on to like where the assignments are. So as you can see, for each day, there is an assignment, and you need to score at least 10 for each day's assignment. So if you are able to score above 10 for the first day, the second day will be unlocked. If you score 10 or above for the second day, the third day will be unlocked, and so on up until the last day. So you have just 3 attempts, and it's timed. Okay, wow. You have a time limit of 60 minutes, and you have just 3 attempts. So the assignments will be open for 2 weeks. So ensure you score the minimum grade during this period. Sorry. So to get the certificate, you need to score at least 75% in total. So at least 10 from each homework, and at least 75% cumulatively to get the certificate. Okay. I don't know if there are any questions concerning this.
I see 2 hands. Maybe people want to ask questions by talking. Should I? Okay, no problem. If you want something, you can use this, as we said.
Okay. Okay, so you are supposed to receive an invitation email. And when you accept it, you'll be directed to the Canvas page where you can register. Okay, so I think we're good, and we can move on to our content for the day. Okay, so for the workshop, we're going to be making use of the open source bronze Qiskit material created by QWorld. And these are the notebooks in bronze Qiskit. So today we're going to be going over classical systems, and I'll just jump right in. Okay, so before we start looking at quantum systems, we want to briefly look at classical systems and how they work. So for a classical computer, the basic way computers work is that they store values. So they have memory where they store values. And then to the values that have been stored in memory, we can apply gates or operators to change those values. So we have gates or operators to change the values we've stored in memory. And finally, we can read out the values we've stored. So for a classical computer, the basic unit of information you can store is a bit. So if the memory of a computer consists of multiple storage locations, a single storage location is a bit where we can store the value of 0 or 1. So okay, so we're going to look at 4 operators that can be applied to a bit that we've stored in memory. And the 4 operators are the identity operator, the negation operator, the 0 operator and the 1 operator. So I wouldn't necessarily say we utilize the 0 and 1 operators in regular classical computers, but we're trying to like build up how operators work, because we're going to be visiting them when we start looking at quantum systems. So for the identity operator, it works such that it doesn't change the input value provided. So if we had 0 as the value stored in our bits, and we are to apply the identity operator, nothing will happen to the value that we stored won't change, so it stays the same. So 0 still stays 0, and if 1 was stored in our bits, it remains 1. Then next up, we have the negation operator. And for the negation operator, it flips the value we provide it to the opposite one, or the other value. So if we are to provide 0, as you can see here, as its input, we're going to get 1 as the output. And if we are to provide 1 as the input, we are going to get 0 as our output. I hope I said that correctly. Okay, then finally we have the 0 operator and the 1 operator. So these operators, regardless of the input you provide to them, they are going to provide a constant value as the output. So for the case of the 0 operator, as you can see here, regardless of the input you provide it, it's going to have 0 as its output. And for the 1 operator, regardless of the input you provide it, it's going to have 1 as the output. So 0 and 1, they refer to Boolean values. So you can think of them as false and true, or on and off. Okay. So we've just briefly spoken about how these operators work, but we're going to utilize tabular representations to see how we move from the input to the output. So we're going to see state transitions from the input or the initial states to the final states. So let me quickly check the chat if there are any questions before I continue.
No, it's about Zoom links, don't worry.
Okay, perfect, thanks. Okay, so for the transition tables, let me show how to read the information from these tables. So up here, as you can see, we have initial states. So for the initial states, these are our input values. These are the values that our operators or gates are going to be applied to. And then finally, we have the final states. So these are our output values, or the values we get after we've applied the operator. So these are the values we end up reading when we're done applying the operators. So for the entries within the table, we have probability values stored here. And for the identity operator, if we look here, we see a 0. And then we have a couple of entries within this column under 0. So the values we're reading here, they are going to be probability values that will tell us the probability of getting a certain number as the output. So here we'll have a probability value trying to tell us that if we are to start off with 0, what's the probability that our output will be 0? Or if we are to start off with 0, what's the probability? Okay, so let me clear this. And here, if we are to start off with 0, what's the probability that our output will be 1? So let me look at the table where the entries have been put in, so it's even more clear. So here we have the transition table for the identity operator. And we're starting off with 0. So let's see, if our input was 0, let's see the possible outputs we could have. So 0 is our input, and we look at the column below 0. And the first thing we see here is a 1. So the 1 here is telling us the probability that we're going to get 0 here as our output. And if we have a probability of 1, it means this transition is definitely going to occur. So that means for the identity operator, if we're starting off with a 0, we're definitely going to end up with 0, because as you can see, the probability of this happening is 1. And here we have, here if 1 was our input value or our initial state, if you look at the column below 1, we have a 1 written here, trying to say the probability that our output or our final state is going to be 1 is the probability value of 1, meaning this is the transition that is definitely going to happen. So if we look here, we're seeing 0, meaning if we're starting off with 1, the probability that we're going to end up with 0 is 0. So this transition will never happen. We can't start off with a 1 and end up with 0. That's why I have 0 written here. So let's look at another table. Okay, so here we have another table. So this is the table for the NOT operator. And we have the initial state here. So if we're starting off with 0, that is, we have a 0 stored in our bit, and we are to apply the NOT operator. Let's see the values we could get as our output. So if we look here, we see 0. So this transition can never occur. So we can't start off with 0 and end up with 0. That's why I have the probability of 0 written here. And if we're starting off with 0, we have the probability of 1 written here, trying to say our final value is definitely going to be 1. So we're starting off with 0, we apply the NOT operator, and the probability that our final value is going to be 1 is 1. So here we have the probability value. And finally, we have the 0 and 1 operators. So if you look here, we have 1, 1 here, meaning regardless of what we have as our inputs, the probability that our output is going to be 0 is 1. So in both cases, the probability that our output is going to be 0 is 1. And here, same thing. For the 1 operator, we have probability values of 1, meaning regardless of our inputs, our final value is always going to be 1. So we have a probability of 1 here and a probability value of 1 here. So okay, I'm still seeing a couple of hands. I don't know if there are any questions.
Hey, Kenneth. So for the people that raised their hands, please ask on Discord so we can moderate the questions and get back to you later on. Or we will ask Kenneth later.
Okay, thank you.
Sure.
Okay, so I have a question for everyone. So all these operators, they are deterministic operators, meaning that if I give you the operator and I tell you the input value, you definitely know what the output is going to be. So which of these operators do you think that, given the output and the operator, you can tell me what the input is? So which of these operators do you think is reversible, or which of these operators are reversible? So you can just type in the chat. Which of these operators? So we've looked at 4 deterministic operators right now. The identity, negation, the 0 operator, and the 1 operator. So which of these operators do you think are reversible? Or given the output, you can find the input. Given the output and told the operator, you can find the input. Okay, so I'm seeing all of them, identity and not, identity and not, identity and negation, not. Okay. Okay, wow. We have lots of different answers. Okay, so thank you. Okay, so let's look at it this way. For the identity operator, if I had 0 as my input, and I'm told it's the identity operator that we've applied, we're going to get 0 as the output. So if I'm told the output and I'm told the operator, this is straightforward. I can definitely figure out the input value. And even if 1 was what we were making use of here, still the same thing. If I'm told the output and I'm told the operator, I can definitely figure out the inputs. Okay, let's look at the not operator. So we're told 0 is the input and we're applying the not operator. I'm going to write an X here to represent the not operator. And the output is 1. So in the case you see here, if I'm told the output and I'm told the operator, I can definitely figure out the input value. But finally, for the 0 and 1 operators, so for the 0 and 1 operators, so if I'm told, okay, so 0 and 1, both of these values, they map to 0. So if I was to retrace my steps, I'm told the outputs and I'm told the operator. As you can see, if I was to retrace my steps, I won't be able to, because there are 2 possible values that could have provided this as the output. So I won't know which one of these was the input value that was provided if I'm told just the output and the operator. So for the 0 operator and the 1 operator, we can't tell the input values given the outputs and the operator. So the 0 operator and the 1 operator, they aren't reversible. And we're talking about reversible operators now, because when we start looking at quantum operators, they are all reversible. So all our quantum operators are reversible operators. Okay, so let's move on to the next notebook. So in the first notebook, all the operators that we're looking at, they are deterministic operators, because we said if we're told the input and we're told the operator, we know the output. We know the output. But now we're going to look at probabilistic operators. And for probabilistic operators, given the operator and the input, we're not certain of the output. Okay. So we have some system here. We have some analogy or system set up here to help us better understand probabilistic operators or probabilistic systems. So here, we're going to be utilizing a coin. And you can think of a coin as a single bit. So we can think of a coin as a single bit, and our coin can store the value of head or tail. So if our coin has head facing upwards, we could say it has the value of head, or it has stored the value of head. And if it has like tail, facing upwards, we can say our bit has the value t. Our bit has value t. Okay, so we even have some mapping here where 0 and head are the same thing, and 1 and tail are the same thing. So if we had, so our coin is our bit, and if it's facing head, we have 0 stored in our bit. And if it's facing tail, we have 1 stored in our bit. And now we can toss our coin. So if, let's say our coin was facing head and we are to toss our coin and it's a fair coin toss. When our coin lands, it can either land on head or it can land on tail. So as you can see here, we were not certain what we're going to get as output. So we could either go this way where our coin lands on head, or we can go the other way where it lands on tail. So we're not certain what we're going to get as our output. So let's look at the transition table for a fair coin toss. Okay, so we have our transition table here. And as we've said, so these are, okay, so what we have here is the initial states. So we have the initial states written up here. And to the right, we have the final states. So here we have the final states. And we said the entries of our table are such that they represent probability values. So if we are to start off with 0, so 0 is our initial state or our input. And what we have below, these are probability values. So the first thing we have here is 1/2. And 1/2 represents the probability that our coin will land on tail, sorry, will land on head. And 1/2 here represents the probability that our coin will land on tail. Similarly, if we are to start off with 1 or tail, and we are to perform a fair coin toss, we have 1/2 here, meaning that's the probability that our coin will land on head. And we have 1/2 here because that's the probability that our coin will land on tail. Okay. So now we have a task, and we have a task whereby we're told to toss our fair coin a certain number of times, and we're to record the number of times you get head and tail. And then we calculate the ratio of heads to tails. So we could try this 100 times. We could try this 1,000 times, 10,000, 100,000, even 1,000,000 times. And we're to check the ratio in all of these cases. So I'm just going to click here for the solution so we see how this works. Okay, so we have a list here with the different number of times we might want to toss our coin. So here we could toss our coin 100 times, or we could toss it 1,000 times, or we could toss it 10,000 times, or 100,000, 1,000,000, or even 10 million. Yes, even 10 million times. And we have variables here to store the number of times we get head or tail. So we have a loop. We have a loop here. And experiment here. We'll start off with 100. So we have a loop that's going to run 100 times, and we're going to randomly pick between 0 or 1. So this is where our coin toss actually happens, where we're randomly picking between 0 and 1, and we're recording those values. So we'll try this for 100, then 1,000, then 10,000, then 100,000, up until 10 million. So when we're done, we're going to calculate the ratio. So let's see the results. So when we tried this 100 times, we got head 47 times and tail 53 times. And this is the ratio we got. Then we tried this 1,000 times. We got head 511 and then tail 489. And this is the ratio we got. So if you look at these two, what we have below here is closer to 1 than what we have above. Okay, so I have a question for the chat. So if we are to keep increasing if we are to keep adding zeros, so now we're at 10,000. Let's say we try 100 million, a billion, and we keep increasing the number of zeros. What is the limiting value when we calculate the ratio? So what's our limit? So do you know? Can you type in the chat? If we are to keep increasing the size of these values, yes, the size of these numbers, that's the number of times we're going to toss our coin. What do you think is the limit when we calculate the ratio for head to tail? Okay, thanks, perfect. So I think we all agree that it's going to be 1 here. So let's look closely at the results we're getting. So here we're closer to 1 than when we tried 100 sources, and at 10,000 we're even closer. So if you look, we're even calculating the difference here, where we subtract 1 from the ratio we get. And as you can see, the difference gets smaller and smaller every time. So the larger the number of sources, the smaller the difference. Okay, so thank you. And okay, so earlier we were looking at the case whereby the coin we're tossing was a fair coin, or we were performing a fair coin toss. But we can also perform a biased coin toss, and that's the table you see here. So for this table, we have a probability of 0.6 here, meaning if our coin was facing head and we are to toss our coin, the probability that it lands on head is 0.6. And if our coin was facing tail and we are to toss our coin, the probability that it lands on tail is 0.4. So as you can see, it's biased towards head. That is it's biased towards head. So the probability that our coin lands on head is 0.6, and the probability that our coin lands on tail is 0.4. And if we are to check something similar, to a similar experiment, but with our bias coin, as you can see, our ratio is, in an ideal case, our ratio should be 1.5, meaning the probability of it landing on head is greater than tail. Okay, so I am going to move on to the next notebook. Okay, so now we're going to look at the coin flipping game notebook. And here. Okay, so in the previous case where we were looking at tossing our coin, there was no dependence from a previous toss. So let's say I wanted to toss my coin 3 times. If I toss it the first time, there is some probability to land on head and some probability to land on tail. So my first toss, there is some probability to land on head and some probability to land on tail. So let's say it's a fair coin toss. So in the first toss, the probability that lands on head is 0.5 and probability that lands on tail is 0.5. So if I'm to perform the second toss, the probability that it lands on head and probability that it lands on tail in the second toss is still 0.5. And then finally, I could perform the third toss. And here, the probability that it lands on head and the probability that it lands on tail is still 0.5. So as you can see, like the third source did not depend on the results I got from the second source. And the second source also did not depend on the results I got from the first source. So there is no form of dependence here. That was from the earlier coin source we just observed. But now in the coin flipping game, we're going to look at a situation whereby there is some form of dependence. So, okay, so let me explain how the game works. We have someone called, or we have a friend called Aja, and she has 2 coins. So she has a euro coin and a cent coin. And she's going to start off by tossing her euro coin. So if you look here, the euro coin has some probability that lands on head and some probability that lands on tail. Similarly, the cent coin has some probability that lands on head and some probability that lands on tail. And as you can, it's from the information you see here, it's clear that both coins are biased coins. So the game works such that you start off by flipping the euro coin, and if the euro coin should land on head, then she's going to flip the euro coin once more. But if the euro coin was to land on tail, then she's going to flip the cent coin. So there is some relationship between head and the euro coin. And there is also some relationship between tail and the cent coin, such that if her coin is to land on head, regardless of the coin she tosses, if it's to land on head, then the next coin toss is going to be the euro coin. And if the coin is to land on tail, the next coin toss is going to be the cent coin. So from what we see here, there is dependence. So if she tosses the first coin, if she tosses the first coin and it lands on head, for example, in the second toss, as you can see, the probability that it lands on head will be 0.6 and the probability that lands on tail will be 0.4. But if the first coin toss was to land on tail, then in the second toss, the probability that lands on head is 0.3 and the probability that lands on tail is 0.7. So the second toss, its operator or its probability values depend on what was gotten from the first toss. Okay, so I hope that was clear. Okay, so I'm just briefly looking if I have any questions. Okay, so I think we're good.
Bruna and Rodolfo are monitoring the questions, so if they have something worth mentioning, or if there is something that is not clear, they will ask, I believe.
Okay, thank you. Okay, so here we have the game we just described. We have some Python code written here to execute this, whereby or even instead of looking at this, let's look at the tree, for example. So let's say I was to start off with head. Sorry, or which is better? Yes, let's say I should start off with head. So head here, I'm saying head because we started off with the, or let me do it like this instead. I'll write euro. So we're starting off with the euro coin, and then we're going to toss the euro coin. So the euro coin can either land on head or tail. So it can either land on head or tail. And if it's to land on head, we're going to toss the euro coin once more. And it can either land on head or tail. So I'm looking at an example whereby we have two tosses. So it can either land on head or tail. And okay, so we toss our euro coin. If it's to land on head, we're going to toss the euro coin once more. And it can land on head or tail. And when we toss our euro coin the first time, if it was to land on tail, then we're going to toss the cent coin. And when we toss the cent coin, it can either land on head or tail. Okay. So for something like this, for the game, after two coin tosses, what's the probability that it lands on head? So what's the probability that it lands on head after two coin tosses if we were playing the coin flipping game? So you can type in the chat. What's the probability that it lands on tail after two coin tosses? So let me scroll down so that you can see the probability values. So these are the probability values. And this is the operator that represents our coin flipping game. So these are the probability values. And after two coin tosses, what's the probability that our coin will land on head? So any takers? Does anyone know? You can type in the chat. Okay, so I'll go over the question one more time. This is how the game works. We're starting off with the euro coin, and the euro coin has some probability of landing on head and some probability of landing on tail.
Hey, Kenneth.
Yes, hello.
Sorry to disturb you, but just to highlight this, I mean, questions, please, guys, just refer to Discord, all right? Because there we have more control about about the questions. So whenever you have a question, just pose them in Discord. Sorry, Kenneth.
Okay, thank you. So we're starting, okay, okay, I get the fact that they should ask questions on Discord, but if I was to ask a question, they can answer here, right? They can answer in the chat here. That's fine.
Yeah, for sure.
Okay, great. So we're starting off with the euro coin, and the euro coin has some probability of landing on head and some probability of landing on tail. So when we toss the euro coin, if it's to land on head, then we're going to toss the euro coin once more. But if the euro coin should land on tail, then we're going to toss the cent coin. And the cent coin has a different probability of landing on head and a different probability for landing on tail. So if we were to do this from two tosses, what's the probability that we're going to end up with head? Okay, perfect. So let me actually try to calculate this. So from the first toss, the probability that it lands on head is 0.6. And then we have 0.6 once more. And then here, the probability that lands on tail is 0.4. But if it's to land on tail, then we're looking at the cent coin. And the probability that it lands on head when we toss the cent coin is 0.3. So we have 0.6 times 0.6. So that's 0.36. And then we have 0.4 times 0.2. So we have 0.12. Okay, perfect. So I think most of the answers were right. So it's 0.48. Okay, so thank you. So that's the main idea of the coin flipping game notebook. So I'll just move on to the next notebook. Okay, so now we're going to look at probabilistic states. So earlier we spoke about these operators. So here we were looking at the case where we're performing a fair coin toss. And it's such that, let's say our coin was facing head. So we have a coin facing head and we tossed this coin. So if we toss this coin, there is some probability it could land on head and some probability it could land on tail. So if we are to just enclose this in parentheses, so I'm even going to write it out here. So we have 1/2, 1/2. So in the case you see here, up here, we have the probability that it lands on head, and below, we have the probability that it lands on tail. What we have here, it's a probabilistic state, which is what we're going to explore now or look at now. And you can think of the probabilistic state we have here as our coin even spinning in the air, with some probability it could land on head and some probability it could land on tail. And this is from a fair coin toss. Similarly, we could also even look at a biased coin toss. So if I was to, let's say, enclose this in parentheses. So we have 0.3, 0.7, and so we had our cent coin and we toss it in the air, and it has some probability of landing on head and some probability of landing on tail. So what we have here is a probabilistic state. So moving on to the probabilistic state notebook. So for our probabilistic states, we just have some vector, and each entry in our vector is the probability that we observe some outcome, or we obtain some outcome. So in the case of our coin, we have just two entries, and our two possible outcomes are our coin landing on head and our coin landing on tail. So we have a two-dimensional vector here, where the first entry is the probability that our coin lands on head, and the second entry we have here. So let me just fill this with variables. So the first entry we have here is the probability that our coin lands on head, and the second entry is the probability that our coin lands on tail. So the thing about our probabilistic states is that because each entry here represents the probability of some outcome, they are all supposed to sum up to 1. Because in the case of our coin, we toss our coin and the only two possible outcomes are it lands on head and it lands on tail. So when we sum all the possible outcomes, we're supposed to get 1. So okay, so here we even have the case of a dice or a die, and here we are to roll our dice. So in this case, we have 6 possible outcomes. We have 6 possible outcomes. And the first one here could be the probability that when it stops with 1. Here it stops with 2, 3, 4, 5, 6. So A here is the outcome whereby 1 is the face on top. 1 is the face on top our dice. And B here, we have 2 on top our dice. C here, 3, 4, 5, 6. So we have 6 entries here. And if we are to sum them, they should all sum up to 1. So another thing we should take note of is that the entries of our probabilistic states, they should be non-negative values. So we shouldn't have negative values in them. So we don't toss a coin, and the probability of our coin landing on head is minus 0.3, for example. Okay, so that's probabilistic states, and we're going to move on to the next notebook where we'll look at probabilistic operators. Okay, so just now we spoke about probabilistic states, and we said we represent them in the form of vectors, where each entry in our vector is the probability of some outcome. But earlier we spoke about how if you had some computer that can store some certain value, we can apply operators to change these values. So if we think of a probabilistic state as some value that can be stored, we can now make use of probabilistic operators to change those values. So we're going to do this such that our probabilistic operators are going to be in the form of matrices, and then our probabilistic states are vectors. And by performing a matrix vector multiplication, we can change our probabilistic state. So let's look at the case whereby we have a coin and our coin is facing head. So we're using a probabilistic state with the entries you see here. So we have 1 here, meaning our coin is definitely facing head. That's the probability we have here. We have a 1 trying to say our coin is facing head. And now we can multiply it with some matrix. So we're going to multiply it with the matrix you see here. So we're going to multiply it with the matrix you see here. And if we are to do this, we're going to get 0.6 and then 0.4. So this is the state we initially started off with, but when we applied the operator you see here, this is what we got. And the thing is that, so we called the operator you see here, the act of tossing our coin. In this case, the act of tossing our game coins. That was the operator we defined with the table you see here. So just by performing the matrix vector multiplication you see here, we were actually playing the game we saw earlier in the coin flipping game notebook. So this is the outcome from the first toss, and we could even try a second toss. So let's repeat this one more time and see the outcome we're going to get from tossing our coin twice in a row. So now if we are to do this, we have 0.6 multiplied by 0.6, and then 0.3 multiplied by 0.4, and then we sum these values. So we're going to get 0.48. And if you remember, when we were looking at the coin flipping game and we performed 2 coin tosses, the probability it will land on head is 0.48. So just by performing the matrix vector multiplication twice in a row, we have the probability that it's going to land on head. And then similarly, we could repeat this with we've calculated what's up here for head, and now we can calculate for a tail, and these values should sum up to 1. So we're definitely going to have 0.52 here. So 0.4 multiplied by 0.6, we get 0.24, and then 0.7 multiplied by 0.4, we get 0.28. And then if we are to sum these values, we're going to get 0.52. So here we have the probability that we're going to end up with tail after tossing our coin twice in a row. And if we wanted to check for the probability of getting head or tail from 3 tosses, all we need to do is multiply the vector you see here by the same matrix. So we just multiply by this matrix the number of tosses that we're interested in. And at the end, we'll have the probability that lands on head and the probability that lands on tail. Okay. So as you can see here, we started off with head, and we're using the coin flipping game protocol. And this is after the first toss, and then after the second toss, this is what we get. So for our probabilistic operators, we don't want negative entries in our probabilistic operators. We don't want negative entries within them. And we want the columns to sum up to 1. So if we are to sum these values, we're going to get 1. So 0.6 plus 0.4, we're supposed to get 1. And 0.3 plus 0.7, we're going to get 1. So we want the columns to sum up to 1, and we don't want negative entries within our probabilistic operators. Okay.
Are we waiting for them to do a task?
Yes, I'm trying to figure out something I can ask. So I think I'll just stick to this. Let me see if I can ask some question here. Okay, so for the operator you see here, okay, so I'm going to call this state 1, state 2, and state 3. So 1, 2, 3. So this is a very simple question. So from this operator, if we're starting off with state 2, what's the probability that we're going to end up in state 3 if we are to apply this operator? So we're starting off with state 2. What's the probability that we end up? So I'm just writing this because I felt this might be like a little small. So I'm just writing it here, so it's a lot bigger. But if we're starting off with state 2 and we are to apply the operator you see here, what's the probability that we end up in state 3? Okay, so I'm saying 30%. Any other suggestions? So we're starting off in state 2. What's the probability that we end up in state 3 if we are to apply the operator you see here? Okay, 0.3. Yeah, perfect. So this is what we started off. This is our initial state. So if we are to apply the operator you see here, and this is the final state that we're interested in, the probability that we're going to end up with this final state is the value you have written here. Okay. So let me move on to the next notebook. Okay, so now we're going to look at 2 probabilistic bits. Okay, so 2 probabilistic bits. Okay, so earlier we were talking about our coins. Earlier we were talking about our coins, and for a single coin, we can think of a single coin as a single probabilistic bit. So we know our bits are two states or two level systems. So we're going to use a two-dimensional vector for this because there are only two outcomes that we're interested in. So if I had something like this, it represents our coin facing head. And if I had something like this, it represents our coin facing tail. And then if I had, let's say, 0.5, 0.5, this represents the probability that our coin lands on head, and this represents the probability that our coin lands on tail. So we have a two-level system here. So it's a probabilistic bit. And okay, so now we have a coin with some probability that lands on head and some probability that lands on tail. And similarly, we can have another coin with some probability that lands on head and some probability that lands on tail. So here we have the probability that lands on head, and here we have the probability that lands on tail. Here we have the probability that lands on head, and here we have the probability that lands on tail. So these are two separate coins, and we can even apply operators to these separate coins and get new probabilistic states. So one thing we might want to do is that instead of dealing with our coins separately, we might want to combine them. So here I have my first coin with some probability that lands on head and some probability that lands on tail. And I have another coin with some probability that lands on head and some probability that lands on tail. So one thing I could do is that I can combine these coins or these probabilistic bits and have some combined probabilistic states. So in the case you see here, I could have an entry that represents the probability that both coins land on head. Another entry that represents the probability that both coins, one coin lands on head and the other lands on tail. I can have the probability that one lands on tail and another lands on head. And finally, I can have the probability that both coins land on tail. So if I was to combine these two probabilistic bits or these two coins using the variables you see here, what's the probability that both coins land on head? So this is a question. Okay, I think someone even jumped ahead of me. Okay, so the probability that lands on head is so I'm seeing AC. Okay, so the probability that lands, okay, so this probability that both land on head. The probability that the first lands on head and the second lands on tail. Okay, AD. Oh, well. And all the remaining entries. So what goes here? Okay, so I'm seeing BC. And the final entry is going to be, okay, so I'm seeing DB, BD. Okay, so it's going to be BD. So for A here, we're going to use A to multiply the entries you see here first. So A multiplied by C, we get AC. A multiplied by D, we get AD. B multiplied by C, we get BC. Then B multiplied by D, we get BD. So let me even replace these with actual probability values. Okay, so I'm going to fill in the entries here, and you can write out what the probabilities here are going to be. So I have 0.60. Okay, let me fill this one first. 0.3. So what are the entries here going to be? What are the entries here going to be? So you can just type in the chat. Okay, so I'm seeing 0.18. Okay, so that's the first entry here, 0.18. What's the next entry? So what's the next entry here? The blank ones are 0, 0, 0, 0.42, 0. Okay, so I think we're just alternating we're just alternating between 0 and 0.42. Okay. So earlier, when we were looking at probabilistic states, I said the entries of our probabilistic states, they have to sum up to 1, because each entry here is the probability of some outcome. So here in the case of tossing our coin, if we are to toss our coin and the probability that lands on head is 0.6, we can't have 0 as the probability that lands on tail, because it doesn't sum up to 1. So the entry here has to be 0.4. That's the probability that our coin is going to land on tail. And similarly here, the entry is going to be 0.7. Okay, so what goes in here? Okay, so 0.42. The next slot, 0.12. Okay, thank you. And then the final, 0.28. Okay, thanks. And if we are to sum these values, you're going to see that to sum up to 1. So here, we're going to get 0.6, and here we're going to get 0.4. And when we sum them, we're going to get 1. Okay, so thank you. Okay, so here we're just representing our vector in linear form. So 0 here represents head, and this is the probability that we land on head, and 0.8 here is the probability that we land on tail. That's for the probabilistic states we have written here. And similarly, we have a new probabilistic state with the same structure. Okay, so let's move on to the next notebook. Okay.
And maybe
just now
a good point. Sorry, Kenneth. Maybe you can
Yes.
say that people can work out the tasks themselves, right, on the notebooks. And if they can't find, we have also the solutions in separate notebooks. And you can try this yourselves, right?
Yes, sure. So we have a couple of tasks here that you can try on your own. So most notebooks actually have tasks, as you can see here. We've even looked at a few ourselves. But in your own time, you can try out these tasks, and the solutions are even provided for you if you encounter any roadblocks and you just want to look at the solution for help. So there are a couple of tasks here you can try out on your own. So thanks for that, Johannes. Okay, so now we're looking at operators on multiple probabilistic bits. Okay, so we looked at the case whereby we had two separate probabilistic bits and we combined them. So we had two separate probabilistic bits and we were able to get some combined system from both of them. So we had a 4-dimensional vector after we had combined these. So we might have a case whereby for the first bit here, maybe there was an operator we applied to the first bit here and another operator we applied to the second bit here. So in this case, let's say we applied identity to the first bit here and then M. So this is the matrix that represents M to the second bit here. If we are to do that, okay, so let's say I applied I here to A, B, I get something new. I can apply M to CD here, and I get something new. And then I can take the tensor product to get the combined system for the final states. But one thing I could do is that I can just combine these initial states and the output I get, I can also combine my operators and apply the combined operator to the combined input. Let me see if there is a way I can write this out more clearly. Okay, so I have some operator. Let's say I apply I to let's say I apply I. Okay, so we used this notation to represent our coin facing head. So let's say I apply I to my coin facing head. and then I apply M to my coin facing tail. So I can take a tensor at this point. So I applied my operator first before I use my tensor product to get the combined system. But another approach could be to combine the operators. So I can combine my operators and then I also combine my states. So, okay, I'll still do this. So I can also combine my states. And then I'll multiply these. So in one case, I can apply my operator to my states, then take the tensor product. And in another case, I can combine my operators, combine my states, and then multiply them. And in both cases, we're going to get the same output. So here, we're going to combine the identity with M here. So we just take the tensor product. So 1 here, we're going to use it to multiply all the entries. And that's how we get what's here. Then we make use of 0 to multiply all the entries here. That's how we get what's here. And then we move on to 0 here. Then we get this. And finally, 1. And 1 from 1, we get this. So the operator you see here, we can apply it to 2 probabilistic bits. And it would be the same as applying these operators individually to the 2 bits, to the 2 probabilistic bits separately. Okay. So the final notebook that we're going to look at today is correlation. So this is the final notebook that we're going to look at today, and tomorrow we're just going to kick off with quantum systems. Okay. So for the notebook on correlation, we have some explanation here by Daniel. I can't pronounce the surname, so I'll keep saying Daniel. Okay. So in the explanation you see here, Daniel's dad prepares lunch for Daniel and his sister. And he prepares pasta and couscous salad. So there are 2 identical boxes. He will place pasta in one box and the couscous salad in the other box. So Daniel's dad prepares pasta and couscous salad, and he places the pasta in one box and the couscous salad in the other box. And these 2 boxes are identical. So when Daniel walks into the kitchen and picks up one box, he takes it and goes off to school. And then Daniel's sister also goes in, picks the other box, and she takes it to school. When it's lunchtime, if Daniel was to open his box and he sees that he has pasta, On seeing that he has pasta, he knows that his sister has couscous salad. And his sister, on opening her box and seeing that she has couscous salad, she knows that Daniel has pasta. So that's the thing about correlation. By having information about one thing, you have information about something else. So this does not necessarily mean if Daniel was to do something to his pasta, something happens to the couscous salad. Like if Daniel was to add salt, for example, now in his pasta, it doesn't mean the couscous salad will become salty. So there is correlation and causality are two different things. Correlation just means that by having information about one thing, we have information about something else. But it's not necessarily causality, whereby one thing affects the other. Okay. So we're going to look at one more explanation here, whereby Daniel's dad has 2 coins. Daniel's dad has 2 coins, and they are fair coins. So the first coin is going to pick it up and toss it in the air. So there's an equal probability that it could land on head or tail. So we use the vector you see here, 1/2, 1/2. So this is our coin. There's some equal probability that it could land on head and tail. So if the coin was to land on head, he's going to ensure that the second coin is also facing head. But if the first coin that he tossed was to land on tail, he's going to ensure that the second coin is also facing tail. So he wants to match both coins. All he does is that he flips the first coin, and then depending on his value, he's going to match the second coin with the first coin. And then he's going to give one to Daniel and one to Daniel's sister. So if Daniel was to check his palm and he sees head, even if he doesn't check his sister's coin, he already knows that his sister has head. And if he was to see tail, even if he doesn't check his sister's coin, he knows that his sister has tail. So this doesn't mean that if Daniel was to flip his coin from head to tail, his sister's coin will also be flipped. It just means by knowing what his coin's value is, he has information about his sister's coin. Okay, so let's use a couple of states and operators to describe the correlation that we're talking about here. So we've already spoken about okay, so we utilized 2 operators for this. First of all, we said we tossed 1 coin, and we've already seen the operator for a fair coin toss. So the operator for a fair coin toss, it's a 2x2 matrix, and all the entries in our matrix have values of 1/2. So what we have here is the matrix for a fair coin toss. Okay. Then the second thing we said is that he's going to ensure that the second coin is in sync, or it has the same value with what the first coin got when it landed. And to do that, we're going to utilize a new operator that we haven't seen before. That's the CNOT operator. So the CNOT operator is an operator that works on 2 bits. We can't apply the CNOT operator to a single bit. It's an operator that works with 2 bits. And this is how it works. So this is how it works. if the, okay, so we said it works with 2 bits. That means it has 2 values as its inputs and 2 values as its outputs. So 2 values as its inputs and 2 values as its outputs. So here, we have 0, 0 as our input. And the 2 bits we have as the 2 bits we have that we're going to apply C0 to, we can assign some certain names to these 2 bits. So for the first bit, we're going to call it the controlled bit. And the second bit here, we're going to call it the targeted bit. So the controlled bit, we're going to check its value. And if it has a value of 0, then we're going to leave the targeted bit alone. You can think of us applying the identity operator to the targeted bit. So if the control bit has a value of 0, we're applying the identity operator to the targeted bit, which is what we can see here. So we have 0, 0. And because the control bit has a value of 0, the targeted bit stays the same. So it's 0 here. Its initial state here is 0, and its final state is also 0. And here we have 0, 1. So our controlled bit has a value of 0. And we're going to leave the targeted bit alone. So the targeted bit is going to stay the same. So here, as you can see, we have a 1, and it stays the same. So we also have a 1 at the other side. But if our control bit should have a 1, then instead of applying an identity, we're going to apply the not operator now to the targeted bit. So if our controlled bit has a value of 1, then we're going to apply the not operator to our targeted bit. So here we have our control bit has a value of 1, and if we are to apply not to the targeted bits, as you can see, we go from 0 to 1 here. And here also, where the input is 1, 1, our control bit has a value of 1. And because of that, we're going to apply the not operator to the targeted bit, and it now has a value of 0. So when 1 is the control, we're going to flip the value of the target. So 0 here becomes 1, and 1 here becomes 0. Okay. I hope that's clear. So with this, we can accomplish we can create the correlated states that we spoke about earlier. So all we need to do is that for the first coin, or the first probabilistic bit, we just need to apply the coin flipping operator, and then we get what you see here. So here we have some probability that it lands on head, and some probability that it lands on tail. We have some probability that it lands on head, and some probability that it lands on tail. And at this point, we can apply our C0 operator. So if we are to, okay, sorry. So our first coin here is like our coin that's been tossed in the air, with some probability that lands on head and some probability that lands on tail. But for our second coin, it's facing head. As you can see, it's facing head. It has a value of 1 up here. So it's facing head. So for the coin that we tossed, if it's to land on head, that is, if it's to land on head, then it has a value of 0. And because our second coin is facing head, or it has a value of 0, we're going to do nothing. So we end up with 0, 0, which is what you see here. So half of the time, we would expect the coin that we toss to land on head. And if it was to do so, because head is 0, we're going to do nothing to the targeted bit, and it will stay 0 also. But let's say the coin that we tossed was to land on tail instead of head. So if it's to land on tail and it has a value of 1, then if it's to land on tail and it has a value of 1, then we're going to apply the C0 operator. And we've already said that the second bit has a value of 0, or it's facing head. We've already said that. So if we are to apply the C0 operator at this point, we're going to get 1, 1. So there are 2 possible cases. We start off with, sorry, our first coin lands on head, and we're going to do nothing. In that case, we have 0, 0 here. And in the other case, our first coin is going to land on tail. And because of that, we're going to apply the C0 operator. And our second coin is now going to be facing tail also. So this is the other possible scenario. So what we have here is our correlated system, whereby either both coins are facing head or both coins are facing tail. Okay. I know I've like really blabbed a lot. I'm sorry for that. So I think we're going to be like concluding soon. So I guess I just have like one more question and we can call it a day. So for the system you see here, I'm going to write it in its vector form. I'm going to write this in its vector form. So we have 1/2 here for 0, 0, then 0 for 0, 1, 0 here for 1, 0, and then 1/2 finally for 1, 1. So this is head, head, and tail, tail, head, head, and tail, tail. Okay, so the vector you see here represents the state you see here. So if I was to do this, and I wanted to split the vector you see here, so this is meant to be some composite system. If I wanted to split this back to our 2 separate probabilistic bits, what are the values for A and B going to be? So I want to move from the combined system back to our 2 separate probabilistic bits. What are the values for A, B, C, and D going to be? So you can type in the chat. So we have our combined system here with head, 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 tail. Tail, head, and finally tail, tail. So we have our combined system here. And we want to split it back to 2 probabilistic bits. What are the values for A, B, C, and D going to be? Okay, so I'm seeing 0.5, 0.5, then 0 and 1. Okay, I'm seeing 1/2 for all the entries. Okay. Any other suggestions? Okay, someone is saying, wait, that's wrong. Any other suggestions? Okay, I'm seeing 1/2, 1/2, 1, 0. Okay, so let me see if I can solve this. So from what we have here, we're saying that A multiplied by C or even before that, let's say, okay, yes, A multiplied by C is 1/2, and then B multiplied by D is 1/2. And then we're also saying A multiplied by D is equal to 0. And then B multiplied by C is equal to 0. So from this, we're trying to say either A or D is 0, and either B or C is 0. But if either one of these is 0, then how can we multiply? How can we make use of one of these values that should be 0? And we have 1/2 as our output here. So clearly, it's a contradiction, and this is not possible. We cannot split our composite system here as a tensor of two separate probabilistic bits. So our composite system cannot be written as a tensor product of its subsystems. So that's one way you can check for correlation. So in correlated systems, we shouldn't be able to split our composite system into its subsystems. And we can even have correlation for more than just 2 bits. We can have for 3 bits, 4 bits, as many bits as you want. Okay, so that's pretty much all our content for today. So I want to thank everyone. This was a really nice session, and tomorrow we're going to be looking at flipping quantum coins and how it's different from flipping our classical coins. So I don't know if yes, thank you, Ioannis. So I don't know if Ioannis or anyone else in the Q Brazil team has anything to add, but I'm done. So thank you.
Yes, I have
Okay,
some.
Okay.
Who said? Okay, all right. I have some points just to remind you guys. Just change your names there in the Discord so we can recognize you. So put in that format like name, your name, and where you're from, if possible, right? And thanks for attending actually to the first lecture in this day. We have lectures for until Friday. So then just stay tuned and pose your questions in Discord so we can, for the next hour, at least we can still manage to answer you, and probably we can get to you also tomorrow. Yeah.
Thank you guys for monitoring Discord and answering all the questions. And I suggest you go through the notebooks yourselves, the tasks there, try out your solutions, and then look out for the cheats on our solutions. And also log into the Canvas course and check out the info there if you're interested in getting a diploma from this workshop. Okay, and thank you all for attending, and see you tomorrow. The same link, the same time. Bye, I'm stopping the recording now.
Thanks, Charles.